So this time it is not about something what Klaus Hasselmann has initiated, but something which was certainly consistent with his thinking, even though in a somewhat reversed way. Namely, the issue is we're talking about the noise part, or the slave part, and how it is conditioned by the signal part, if you want to use Hasselmann wording. So concepts of downscaling. And so let's start with the scaling cascade of climate models. So here, actually, this is from your old group, Angelica, on the left-hand side. It was an experiment which was done by Günther Fischer some 30 years ago. And he was studying the development of the general circulation in, how can I get this away? On an aquaplanet beginning with the state of rest. And I think it was a fine paper. So you see here on the left-hand side, the zonal wind at 950 hectopascals zonally average. And here, And here the meridional wind, and then the first 60 days. And this is from the South Pole to the North Pole. And during the first 10 days, nothing was happening. And then suddenly something happens, mumble, mumble, small things. Here's already something a little earlier. And so it takes a while. And then it fully develops what we want to see with the cells, and the general circulation is sketched in this diagram here. So it takes something like 30 or so days that from nothing you get this circulation. So, I mean, that means also that these regional features have nothing to do with specifics on the surface, because we are on an aquaplanet, but is essentially the response of something happening on the globe to the differential heating. No. The next diagram shows you the long-term mean of the zonal wind at 200 hectopascal on the left, geopotential height in the middle, and the bandpass filtered variance of 500 hectopascal geopotential height, often named storm track. And here you see, obviously, that there are geographical features, but the broad things are essentially given by the major mountain ranges and the distribution of land and sea. Also here, regional details really do not matter. And regional includes something like irrelevant mountains like the Alps or something of that sort. So this is essentially the response of what I've shown before, the global features, and then these large-scale geographic features. And if we go then one step further, these are composites of air pressure on the left-hand side and zonal wind on the right-hand side. For the day before, intense precipitation in Sacramento, value that's given by the red star, and on the day of maximum precipitation. And why I said middle, I don't know, very likely there was a bit more. It means here the lower one. And it's the average of the 10 most intensive precip events. And so you can see that indeed the fact why it is raining in Sacramento is because we have a low pressure system coming closer from the Pacific Ocean and at the end of the jet stream. So it's again so that the large scale determines something what happens on the small scale. And so the main statement here is that regional climates do not make up global climate. That is very different from what geographers, climatologists in the 19th century thought. In those days, people went out into the world to map the climate in all parts of the world, and in the end, they came up with a with maps, global maps of climate, and they were made up of the sum of the regional maps. But instead here, regional climate should be understood as a result of an interplay of global climate and regional physiographic detail. So the local processes are important for the formation of the global climate, indeed, but not in their details, but through their overall statistics. So that means we can model planetary scale climate with dynamical models with limited spatial resolution. I mean, already in earlier times, we had climate models which are rather coarse resolution, 5 degrees grid distance or so, and they got the main things right. So the smaller scale things are not necessary to know in any detail. It means, of course, also that the success on planetary scales does not imply success on regional or local scales. So when people look at say, maps of scenarios of future climate change, and so they get a global map, and then they're trying to find out what happens to Italy, southern Italy, then this is not the right way to do, because southern Italy is not well resolved. And third one, the effect of smaller scales can be described summarily through parametrizations. Now, how is it in models that what we include? So we have here the typical time length scale diagram showing what type of processes we have in the atmospheric system, from planetary waves to microturbulence, and it is along a diagonal stretching from 1 second to 10 to less than a meter or so, up to more than 1,000 kilometers, thousands of kilometers, and a characteristic time of several months or so. But if we look in our models, then it's only the light part which is resolved. The other part, cumulus convection, if we go for global models at least, boundary layer, turbulence, and so forth, they're all parametrized. They're not explicitly given. And that's quite a miracle that we can do so, that we are successful in simulating planetary waves, cloud clusters, and cyclones relatively well without having all the other stuff. And this shows why such models of the general circulation of the atmosphere and of the ocean are so much more successful than, say, ecological models, marine ecological models, because you cannot draw such a map. Now, if we come to the concept of downscaling, and this is formally given by this little, I don't want to call it equation, namely that the small-scale climate, that's the statistics of some weather variables, is given as a function of two things, namely the large-scale climate statistics, or the climate state, and psi s, that's the small-scale physiographic details. So if you know the large-scale climate state and you know the small-scale physiographic details, then you can derive to some extent the small-scale climate. Now the F is, of course, the problems. Which are, how do we summarize the climate? They may be parameters, statistics of dynamical state variables, say stream function, temperature, pressures, or impact variables. That's particularly interesting that we can use these also impact variables, such as when snowdrops flowering in Schleswig-Holstein. And F is a statistical or dynamical. Dynamical means process-based model. Now let's start with statistical downscaling. I'm referring to a paper of some 25 years ago, where we dealt with storm surge statistics in the German Bight. In those times, we did not have these nice transient scenarios, but we just had a doubling of CO2. So in this case, what we want to know is the statistics of high tide water levels at Cuxhaven. And here we have the time series of these quantities, namely the 99 percentile. So 1% of all surges are above that per year. 90 percentile, second curve on top, that means 10% of all surge water levels up above that, 80, 50, and 10%. And we have subtracted the linear trend of the annual mean. There's a substantial annual trend which has hardly anything to do with climate, but is essentially related to modifications of the river. So this is the quantity we want to specify. A vector of these statistics, annual statistics. And so we did that by using a canonical correlation analysis, which relates one set of vectors to another set of vectors. And one set of vectors here is S, that are the coefficients of the first four empirical orthogonal functions of winter. So we are using winter monthly mean air pressure distributions. So we use as predictors the monthly mean fields of air pressure. Note that monthly mean air pressure has no dynamical relevance for water levels in Cuxhaven. It's the daily air pressure, but not the monthly mean. On the other hand, we have the vector series Q, which is three-dimensional, featuring the 50, 80, 90 percentiles of winter intramonthly storm-related water level distributions. That is what I've shown you just before. And so then we expand both S, that is the air pressure fields, and Q, that are the 3 percentiles of water levels in Cuxhaven, into a series. And then they go with as a sum of a coefficient and a pattern. And canonical correlation analysis determines patterns so that the coefficients have maximum correlation. A S1 and A Q1 have maximum correlation. A S2, A Q2 have maximum correlation after subtraction of the first component, and so forth. And so the analysis tells us which anomalous monthly mean large-scale pressure anomaly in winter over the North Atlantic is associated with which intra-monthly anomalies of 50, 80, and 90 percentiles of stormwater variations at Cuxhaven. So we are rating one set of statistics, namely monthly means, to another one, intra-monthly percentiles. The results are shown here. So on the left side, you see two maps of the North Atlantic, and they show the first two canonical correlation patterns of the predictor, in this case, the air pressure field anomalies. And on the table on the right-hand side, top, you see the canonical correlation patterns for the intramonthly water level variations. So you can see here, K equal 1, that is this left diagram here goes with the reduction of the mean of the 50 percentile of water level variations, and reduction by 20 centimeters, the 80 percentile by 16, and 90%, sorry, the 19% by 18 centimeters. And it goes with I forgot what epsilon K is. It goes with the correlation of almost 90%, but this is biased because of the canonical correlation. On the other hand, this pattern here shows you that it has a maximum far out there, that the percentile, the 50 percentile goes down, and the 90 percentile goes up. If this is really a stable feature, that's another story. But if we use these two patterns here to predict what the 90 percentile variations, what the variations of the 90 percentiles in Cuxhaven should be, then we get this result, and you cannot see it very good. The solid line is what had been observed or reconstructed from observations. The dash is from the monthly mean air pressure field. And you see it is, or you have a hunch that this is relatively close to each other. In case of this first pattern, the explanation is relatively nice because you can see that the storms would travel, so the anomalous storms would travel along this gradient. So if we have high pressure sitting here, low pressure sitting there, then fewer storms would travel along this way. It would push less water to Cuxhaven, while if there's the opposite situation with the high pressure system here and a low pressure there, then we would have traveling more of these storms. By the way, there's something which would be really nice for visualization. And I saw a movie of that once a while ago, namely when you plot the low frequency filtered air pressure field or 500 hectopascal field for an extended time. And on top of that, the filtered, the high frequency part of the pressure field filtered, then you can see that these blobs of the high frequency part, mostly associated with storms, travel very nicely along the gradients of the low frequency part. I mean, it's like an autobahn or so. I wonder if that should be redone. So this was a movie which was prepared by NCAR in the 1970s or so. So there's room for getting it nicer. Anyway, so this is the Fmap we've constructed here. And here we have two examples. So the January 83 is a case when we have a large negative coefficient of CCA1. That means we have a general increase of the whole distribution. And in December, we see we have a large positive one, and it is moving downward. So that is, and this is what happens within a month. On the other hand, if we go for a large second coefficient, positive and negative, we have what we see on the right-hand side. So in case of, and the second pattern described a lowering of the mean state, of the mean water level, but an increase of the high percentiles. And so the dash curve describes just that, while the solid line describes the opposite, namely an increase of the mean level, but a decrease of the extremes. And that's what you see here. So that works quite nicely. Another case I have here is using a conditional weather generator. This is work which I did with Aristida Buzuia from Romania, and so this is almost 20 years ago. So what we did here is a rainfall generator is a stochastic process which mimics the behavior of rainfall as a sequence of either wet or dry days. And the simplest rainfall generator makes use of 4 parameters, namely the probability to have a wet day following another wet day. That's P11. The probability that we have it wet after it was wet yesterday. But the other one is the probability to have it wet day following a dry day, P01. And so these are 2 parameters. And then if we have a wet day, then we assume that the amount is described by a gamma distribution with 2 parameters, k and beta, with a shape parameter k and a scale parameter beta. K times beta is the mean across all days which are wet, and I've shown here a few curves of the different distributions. Otherwise, I have no good understanding and feeling for the gamma distribution. So this is what we want to fit to what we want to estimate given an air pressure field, mean air pressure field. And so this is, we made a CCA, so the predictor is the monthly mean air pressure field. And the predictant are these 4 parameters, P01, that is, it's wet after it had been dry, P11, it's wet after it has been wet, and the mean value, and K I cannot really understand. So, and this shows the first CCA, namely if we have a high pressure system, and it's winter again, I think. We have a high pressure system sitting over, what is that? Northern Italy, and then into a low pressure system somewhere near Moscow or so. And we see if we have a flow which describes a easterly, which is southeasterly, then we tend to have fewer wet days after a dry day, fewer wet days after a wet day, and an overall less wet days. And of course, the other way around. So that makes sense. And if we then try to use this model based on the canonical correlation analysis, we can see to what extent this is reconstructed well. So we have a dashed and solid lines here. Solid is the observed part, and dash one is what the canonical correlation analysis says. And obviously, it is doing it quite nicely. And note, on the other hand, that we are operating here all the time with data from a really long time series, 1901 to 1999. So this is based on station data. These were two examples for statistical downscaling, two non-trivial examples. Of course, originally we had also simpler ones. Now we notice that we can indeed also think about dynamical downscaling. In that case, the F is a dynamical model, motivated by physics. So let's first start with the conventional setup. And regional atmospheric models, they serve the purpose to describe the dynamics at regional and smaller scales well. And ideally, regional models would return one unique solution given a set of boundary values. This is not the case. Mathematically, there's no unique solution for a given set of each boundary values. The point is, the problem is not a boundary value problem. It's not a boundary initial value problem. There is a numerical problem, namely that the wave propagation velocity depends on the grid resolution, so that waves traveling within and outside the limited area will arrive at the outgoing boundary at different times. This problem was solved by suggesting the so-called sponge zone in 1972 by Hugh Davis. But this is not the overall problem. So this is not giving us unique solutions. The physical explanation for the fact that we do not have a unique solution is that in the interior of the domain, developments independent of the lateral conditions may create large anomalies. And this is in the spirit of the stochastic climate model. What we need some noise, and we need some memory in the system. And if the boundary values are not so strong that they flush away any anomalies forming, that means that the memory in the internal part of the system is large, then we see that different solutions can emerge. So the sponge zone does not solve the problem of the non-existence of well-defined solutions of the boundary value problem. However, if the domain size is small compared to the travel distance from the boundary to the interior, we will not see significant anomalies in the interior. So it's really a question, how much time does the system have to develop something of its own? An important experiment, which was done in 2002 by the group of Dennis Laprise, was the so-called Big Brother experiment. So what they have done is they have a Big Brother simulations with a high resolution, covering a regional area or global, and then a sub-area is cut out, and constant values of the Big Brother at the boundary are prescribed. Then the limited area is run, model is run. So we have a complete description of what is going on, then we cut something out, and use then the quotient values. And it turns out, at least in case of strongly flush flow, that the small-scale dynamical features of Big Brother reappear in the limited area model simulations, even though the Big Brother was quotient at the boundaries. Now this is demonstrated here. We have on the left-hand side the Big Brother, which is supposedly the truth. And you can see that is say the central and eastern part of the United States plus Canada plus a little more. And the rectangle is this color area, the little brother. And so on the right-hand side, you see what happens in the little brother. Outside of the box, we have the same in the right-hand column and in the left-hand column. So you have to compare what happens within the box. So if we are start at the beginning of the simulation, we see that in what the big brother did is you have a hunch that something similar happens in the little brother. But if you go on in time, then after 48 hours or so, the features, the details in the little brother are very similar to what happens in the big brother. So even though in the big brother, in the little brother only knows about the quotient values along the box. So the regional model is indeed able to reconstruct what should happen in the interior, and that's essentially showing that this downscaling works out fine. So I think that was a pretty good and important paper here. But we have this problem that the solution is not unique. And one of the first papers describing this was by Rinke and Dietloff in 2000, which ran a regional model in the Arctic. And and the interesting point here, yeah, and they had two interiors with different resolution. And so then they ran several of these realizations, and then they found out that in the different realizations, they have different solutions or different developments. And this is demonstrated by the internal variability in the two diagrams, one for the larger block and then also what happens in the, if you go for the smaller block. So the variations for the larger block are quite substantial. For the smaller block, they're smaller, but they are there. And so I spoke about that before, that the boundary value problem is not a well-posed thing. The interesting thing, of course, is how this ensemble of solutions would look. And if somebody in the audience in the Meteorological Institute would have an idea how to do that, that would be a great thing. And I'm not aware of a solution of that problem. We reproduced a similar behavior, and I showed that before in the last few years, when Beate Geyer considered an ensemble of limited area models covering Central and Northern Europe, running with observed boundary conditions for several years. And the diagrams here show only what happens within 1 year or one winter. And the two ensembles were generated in this way, that one operated with shifted times of initializations, but otherwise identical conditions. So let's say one started on the 1st of August and the next on 1st of October. And the second ensemble was run with a set of identical conditions, but run on different platforms. So on computers at different places. And here we have the air temperature development in Oslo, and in the four ensembles, and the mean value across at each time is subtracted. And you can see what happens is in both ensembles, on top the initial time ensemble, in the middle the platform ensemble is essentially the same. Namely that we have a tendency to form large anomalies after day 310 or whatever it is, and but that we have hardly anything from 270 to 310 and so on. And if we summarize the two diagrams, we arrive at the diagram at the bottom, which shows the standard deviation at each time for the different ensembles, and they are virtually identical. So that means they are really different developments. When we ask, can we estimate when this happens? then we found that if we build a composite for those cases when the standard deviation is particularly low or particularly large, right side, then we see that if the standard deviation is low, that we have a pretty well-established zonal flow throughout the entire area. And notice that the diagram I showed before refers to Oslo, so that's right at the gradient of that. While if we have large deviations, we do not have a real through flow, but the flow is somehow blocked. And so conditions, when the strength of the zonal through flow is large, then we have little macroscale divergence, while when these disturbances march with a slow speed into the interior, then diverge, which is again an indication that something like the stochastic climate model is at work, namely that you get variance, large variance if the memory is large, while you get small variance if the memory is small. And so on the left-hand side, the memory is small because everything is blown away, while on the right-hand side, there's a chance for disturbances to live for a longer time. The other interesting part of this experiment is, of course, that it does not matter how the noise is brought into the system. So, yeah. Now, the next point is that the dynamical downscaling, but this time with large-scale constraining. So I claim that mathematically, a mathematically well-posed approach to regional climate modeling is achieved when the task of describing the dynamics of regional and smaller scales is formulated as a state space problem, conditioned by large scales, and not as a boundary value problem. And so let me just sketch this with these two formulas. So we have two equations. One is a state space equation, namely that the state at t plus 1 is given as a function of state at t and some external parameters plus an error term. And then we have an observation equation which relates the state variable psi to the observations dt. And then we have an operator g, and again, here are some errors, delta t. And we integrate these forward, and you can do that in more and less intelligent ways. You first ask, given the state today, psi t, what does the F model suggest the state should be tomorrow, psi t star? And then we ask, what should be the observation of this dt star, t plus 1 star? And then we decide our best estimate for the state tomorrow is this preliminary guess, psi star, plus a correction term proportional to the difference in the error of predicting this, the observations. And you can put large efforts in how to define the k. Well, that doesn't matter here. Now, how is it in general if we look at in the output of a dynamical model? Then we have spatial scales for a certain range, and we have large variance usually for small scale, large scales that are on the left-hand side. And for small scales, you have less variance. And so if we consider what is well resolved, then there's a certain critical line here. Yeah. And you would say scales which are below that are not well described, and what is above is well described. I mean, this is disturbed also by the interrupted energy cascade here and so forth, and we do not really know where this line is. So some people say 4 delta for grid scale, grid distances, but that's just gut feeling, and I don't know simply. So that is, if we look at the output of a global model, we should essentially go after these scales, not these here. Now, if we go to a regional model, then we have again this variance distribution. And now only look at to the right part, we have the same situation, namely that the smaller scales are insufficiently resolved, but that the larger scales are well resolved. And so the smaller scales we should not look too carefully at. So for instance, when people look at regional models for grid point data, that's a little bit of a problem. But the yellow part here was already resolved by the global model, or whatever it is. But here we had insufficient resolution for the global system, but well resolved for the regional system. And this is where we have the added value of regional modeling. Here we have something which is better than we had from the global model. Not necessarily here. Again, we do not really know where this line is. So what is the expected added value? We expect statistics and events on scales which are not well resolved for the global system, but sufficiently resolved for the regional system. In particular, we expect an increased variance on smaller scales. We do not expect an improvement of the dynamics and events on scales which are already well done by the global system. I mean, that was something in the beginning of regional modeling, in particular Bernhard Mackenauer, who was in Hamburg and was one of the great pioneers of atmospheric modeling. Among others, the inventor of the transformation method, making spectral models possible. Unfortunately, he's almost gone, which is a shame. Anyway, he always thought that we should get a massive improvement using regional models, say, for large-scale features. This never really turned out to be right. And I would also not expect so. So the useful quantities which we should check if we have such a simulation with the regional models, not for weather forecasting, but for an extended time. So we should make sure that the large-scale state is similar. We should have an unchanged variance of large scales, but we should have differences on regional scales and increased variance on regional scales. The distribution of quantities in physiographic complex regions should be better. We should have better extremes, and we should also have better regional dynamical features such as polar lows, tropical storms, or medications. And so with the, let's see, in case of the spectral, I'm not really explaining it well. Okay, I should have said it here. So in the spectral nudging case, what we do is the observations are not local observations, but are the large-scale states of reanalyses. So that's very different from normal data assimilation where we have point values. Here we say it's the larger scales, which we tell the system it should follow and invent the smaller scales part in a consistent manner. And the dynamical part, that is when here in this part, we apply the spectral nudging. So here, the system should not deviate, but we should have the added value here, while this is somewhat questionable. Now, we did that for subsynoptic phenomena, and that was a simulation done in the early, almost 10 years ago by Fei Chen, using studying polar lows in the North Pacific using a regional climate model. And we had a grid resolution of 0.4 degrees and used spectral nudging. That is, we constrained winds above 800 hectopascals and for scales larger than 800 kilometers. And we were interested in the simulation of polar lows in the northern North Pacific. And here we have an example. So here we have the output of one case, and here we have a satellite image to that we actually got here these disturbances, these two disturbances in the simulations which were not present in the driving and separate analysis. So in this way, we could reconstruct development of the number of detected polar lows in the North Pacific per polar low season. And we see there was a slight increase, but not an accelerated one in later times. The other example is the improved representation of forcing fields for impact models. In this case, we used the regional model REMO in Europe with a grid resolution of 0.5 degrees. Quite a while ago that we did so. And we used also spectral nudging, wind above 850 hectopascal, scales larger than 800 kilometers. And this was run from 1948 to 2010. And we used wind and air pressure to drive models of sea level and circulation of marginal seas for describing currents and sea level. So the output of this model was used to drive impact models. And I'm showing only the statistics of surface waves, ocean waves, and coastal seas. And here we have this somewhat nice result. Keep in mind, these are climate simulations. These are not somehow initialized or so. I mean, they're initialized 40 years ago. And here you have at a buoy, at a location next to Helgoland, the development of significant wave height. And in blue, you have what the model, the wave model, is suggesting. This is run by this by the output of the regional model. In red, you have a buoy sitting, which was taken out in about the 20th or so of October. And in yellow, we had a radar sitting on the beach. And so first of all, the lower diagram is the wave direction. So first of all, you see that the VAMOS radar and the buoy are having about the same results. But you see also that the model is reproducing what these instrumental data are indicating quite nicely. Now you have to keep in mind, what does the wind data we are using here, which information is it carrying? So it knows about the ansatz reanalysis, which is a really coarse resolution thing. So it knows it doesn't know anything about Helgoland. It knows nothing about the German Bight. It knows possibly something about the North Sea, but only really marginally. And so it also doesn't know how far away this point is from the coast and whatever. And on top of that, we have used but we have told the large-scale state of these reanalysis to this regional model, and then we have told the model to estimate what would be the consistent winds given the land-sea distribution on a 0.5 degree. And it turns out it is reproducing it quite nicely. So we thought this is really kind of surprising. So to come to the last part, this is also a bit newer now. It was done essentially by Schubert-Fresius, namely that we thought we can do downscaling, this dynamical downscaling, not only in regional models, but we can do it in global models. Action and idea by, I forgot his name. Oh, by a Japanese guys working with scripts. So we adopted this concept, and we used the ECAM6 T255 and worked with a grid resolution of 50 kilometers. We prescribed sea ice as lower boundary conditions and also sea surface temperature. And we used spectral nudging towards large-scale vorticity and divergence. It was with a resolution of T30 of NSAP1 reanalysis. So we used the coarse analysis of NSAP, truncated it to T30, and prescribed vorticity and divergence in this extended simulation with a T255 global model. And here we have an example. So on the right-hand side, you see what the NSAP was suggesting for East Asia. And on the left-hand side, you see what the model made out of it. And you see essentially the same features, but the patterns are the gradients are stronger, the patterns are better developed in the left-hand side. Now, when we ask on the day-to-day basis, where is the output of this globally downscaled system better than compared to the era interim? So that's a different analysis, an independent analysis for the decade 1999 to 2009. And so here we calculate the prior skill score. Whenever it's red, then the downscale part is better. When it's blue, it is not. And you can see whenever we have strong physiographic details, then the downscaling is doing better. But it's not better on the open sea, in particular when we have no specific force. An example is also the extratropic storm Christian from 2013. And so on the left-hand side, by the way, this is a scientific visualization done by the German Climate Computer Center. And yeah, I have to admit that. So this is the storm as it was simulated in our global downscaling on a certain day. And if we look at the tracks of these storms in three different products, we have the German Weather Service in blue, we have the global downscaling in, what is that? Red, kind of red. And if we use a regional downscaling, it's in yellowish, and you see that's essentially providing the same thing. The regional downscaling has a better grid resolution. So this data set, this ends the global part, and now what can we use all this for? And we go back to the downscaling with the Waymo model, the 50-kilometer grid for Northern Europe, which I've shown before. And here, what we got is we have long-term high-resolution reconstructions, namely 60 years of present and recent developments of weather-related phenomena in coastal regions, as well as scenarios of future developments for 100 years. So that's what we could reconstruct for Northeast Atlantic and Northern Europe. So this is the data set COSTAT. And so we could assess the changes in storms, in ocean waves, storm surges, currents, and regional transport of anthropogenic substances. And later, we extended it to other regions and ecological parameters. The data set is used by many authorities with responsibilities for different aspects of the German coast. Also, economic applications by engineering companies, offshore wind potentials and risks, and shipbuilding companies, and also for public information. And here we have a typical example. So ship design, that is the Flensburger Schiffbaugesellschaft, who were planning for ships to be used on fixed routes. And so they were interested in the statistics of the wave climate along these routes, and the design so that the ship would withstand this, could live well in these wave climates. Navigational safety is another thing described here somehow. Offshore wind, obviously, here. The interpretation of measurements, oil spill risk and chronic oil pollution, where would oil be floated to? Ocean energy, here for instance, an estimate how much currents by tidal power plants could be obtained. And then scenarios of storm surges, conditions, and future wave conditions. So the data set has been used quite extensively by a large variety of institutions. Now to come to an end. By the way, the scenarios which we used in downscaling in this COSTAT were not spectrally nudged, because in that case we do not want to suppress the ensemble variability. Now, conclusions are downscaling to understand, we suggest to understand the regional climate or impact problem as a conditional random process and not as a boundary value problem. So we condition what happens in the interior by some information. And the regional variability is composed of externally enforced variability and internally generated variability. So we have both sources. which is a fact which had been overseen by the most regional atmospheric modelers until the early 2000s, and by regional ocean modelers until almost today. When the internal variability is undisturbed by lateral boundary conditions, it may grow to significant scales and intensities in the spirit of stochastic climate models. So if the boundaries are far away, or the dynamical link, I mean the time to travel from the boundary to the interior is large, then it may grow. And we can use spectral nudging as a way to implement downscaling, namely that we say we prescribe the large scales, and we use the information about the large scales to infer something about the small scales. Indeed, if you are going to conventional regional modeling, this is not a downscaling, because you are not filtering first the system to give the full information about reliably described scales to the system, but you give information along the boundaries. So spectral nudging allows for reconstruction of past variations with limited unchecked internal variability. So it's only, we still have some internal variability, of course, but not that much. And we get something like a low effort. Spectral nudging is not necessarily good for scenario constructions. I have not discussed that. But we could say, if we think about scenarios, we have suggested how the large-scale state could change. But these large-scale states have been developed without any links to the regional scale. So we would really like to know how the regional scales can develop in the interior. And so they can develop independently in various ways. So it represents a range of uncertainty which we want to know in scenario constructions. And this ends my presentation, and I hope that some people are left in the audience.